Good morning. My name is Reda Hajjaji. I'm working in DBT as a research engineer. DBT is the coordinator of Fast in Charge project, and mainly we are working on design of the static and dynamic charging station. We are also involved in other tasks like the energy management system and the communication architecture. So today we'll present an overview of Fast in Charge. Fast in Charge project is supported by the European Union's 7th Framework Program. The starting date was the 1st October 2012, and the end date it will be 13 September 2015. Duration of the project is 36 months. The maximum AC contribution is about 69%. The project is led by 9 partners. DBT is the coordinator, and we have also Technical University of Gabrovo, Automotive Cluster from Slovakia, BADS and Technalia from Spain, Oil Quality Douai from France, and Fiat Research Center from Italy, and ICCS from Greece. Objectives of Fast in Charge project is to develop and demonstrate a complete charging infrastructure in order to address consumers' acceptance of electric vehicle by getting rid of the autonomy issue. Test the implementation and assess its easy feasibility, optimize the energy delivery to station and its interaction with the grid and vehicles, study the impact of its integration in the urban environment to foresee eventual problems that would occur in the frame of real integration. The solution will be integrated in the same vehicle than Unplugged. It's a vehicle daily. The main expected results, it's development of one primary plate to be integrated to one vehicle, development of 2 charging stations, static and on-road, to be integrated in the city of Douai, optimization of the energy management system, and the other main expected result is to demonstrate the efficiency and the viability of the solution in real life conditions. Also to study the exploitation of the solution and the integration in other vehicles and situations. The main expected results, the rated power input is about 30 kilowatts. The gap between cores is 100 millimeters for fast charging. Charging time for 90% of batteries about 30 minutes, and the transfer efficiency it's between 87% and 92%. The boundary misalignment is between 200 and 300 millimeters. The work program is divided on 7 work packages. The first work package is specification. Second is development of static and on-road fast inductive charging infrastructure. The third work package is the development of integration solution, and the third work package is integration and prototyping and testing. The fourth is demonstration and impact analysis, and the sixth is dissemination and exploitation, and the last work package is management. Here in this slide we can see an overview of the topology of the IPT charging station. We can see the converter model, the primary and secondary coil, and the output charging current with the regulation via primary side inverter. On this slide, it's a focus of the main structural components of IPT. We can see the design and the main components of the primary and the secondary coil. Here we can see the it's a representation of the important parameters used for IPT coils for the design and calculation process, like the coupling factor, the quality factor, the surface between coil, the mass of the IPT, the volume, and the current in both coils. This picture shows the main component of the IGBT inverter. We can see also the PCB-based inverter bus bar, the FPGA control system, the air cooled, the 5-gate drivers for each models. And here is an overview of the charging station side for static and dynamic charging. And we can see also the placement of each model, like the input filter and protection, HGBT inverter, and the matching and the compensation models. In this slide, you can see the compensation and the rectification model, which are designed in order to have a small volume and mass, a high efficiency up to 98%, to have also a high level of protection against dust and moisture, output differential current and voltage measurement, and self-diagnostic and cooling control. The specifications and the technical requirements take into account 3 elements regarding the infrastructure. The first element is the infrastructure, and it has to take into account the road features for vehicle. It's the space available and maximum speed charging. The third element to take into account is the IPT model, like regarding the dimensions of the secondary coil and weight and air gap between coils. This slide shows the first approach of the technology integrating the different elements and design in the lowering mechanism. So we can see the main components contains the lowering mechanism, like the secondary coil, the guidance system, the rolling system, damping system. This picture shows the sequence of upward movement of the secondary coil within the prototype. And for the energy management system, the main objectives is to monitor the operation of the charging station, to have enabled the remote control of the maximum charging rate of the station under emergency network operational conditions, user awareness of the location, the availability and the electricity costs of the fast inductive charging station, and offer booking service of AV owners. The end of the project will be at the end of the September 2017. On road and static charging will be tested in a real urban environment in the city of Douai in France. Thank you for your attention.
Thank you, Reda. I think we have, in principle, time for 1 or 2 questions. Is there any question? Martin?
You've shown your core design, and you have reduced the current in the
I didn't tell you. Could you repeat?
You have shown the core design. If you can showed on the presentation at the beginning. I've seen you have reduced the ferret. Here, you can see it.
And this one?
Have you simulated the behavior of the fluxes?
The behavior of...
Here you can see the air gap.
yeah,
It's not concentrated overall.
yes.
Have you simulated this?
Yeah, we have made some element finance simulation of the boat course.
And you can compare the efficiency with complete ferret to your
Yeah,
approach?
yeah.
And
And with the ferret, it's best. The efficiency is best compared with the course without the ferret.
is 1%, 2%, 5%?
I don't remember the exactly how, because another project partner who is working on this point, but I think it's we have a good difference between with ferret and not.
Okay.
Small question. Do you think that it's really practical solution for the future that components have to move from the vehicle side?
For passenger car, not. No, it's not.
Other vehicles, it's okay.
Maybe it's the first step, and we can, after thinking with another solution, more optimize it.